Thank you, Dr. Ghosh, and thanks everyone for coming along on the day two of the conference. And I'm very delighted to come back to India and contribute some of the expertise and experiences I have gained over the years working in Australia, India, and Antarctica. Um, so as introduced, I am Meenakshi Arora, Professor of Environmental Engineering at the University of Melbourne, and I have also additional role of being Associate Dean for Graduate Research. And graduate research means the PhD student. So I've been quite passionate about connecting with India for research because we might feel that there are lots of lessons to learn for India from Australia, but at the same time, Australia is facing similar problems. Population is growing and we have similar kind of challenges. So there is a lot to learn from each other. And today I'm going to tell a little bit of story about some of the projects I'm currently involved with. Okay. So I don't think I need to tell a lot about the groundwater as a resource and how it helps us to sustain life. Millions of people globally rely on groundwater for their drinking water supply. Majority of agriculture use globally relies on groundwater. It provides a very useful source of water for the groundwater dependent ecosystems, the wetlands, the heritage listed sites which protect our endangered species largely receive their water supply from groundwater during the dry periods, and it's source of flow for many streams as well for the dry periods. But generally, we just assume that groundwater is not prone to contamination, generally considered safer than surface water, but as we all know, that's not the case. Groundwater is prone to various contamination sources, natural as well as anthropogenic. So I'm not going to read the whole list, but it just provides a bit of overview of the type of sources which can lead to groundwater contamination. And what that means is groundwater is a universal solvent. Water is a universal solvent, so is groundwater. So everything to some extent will dissolve in water. So at what stage we say it is just the natural or background concentration of a solute or it's a contaminant. And to define it as a contaminant, there are a few characteristics we look at, that it's mobile in groundwater, and solubility is a good predictor that it will move with groundwater. If the solute is persistent in groundwater environment, which means it's not going to disappear in a reasonable time frame, and the reasonable time frame is that the time frame within which it will be picked up and used by someone. The third thing is it is toxic or carcinogenic or mutagenic. So if it ticks any of those three boxes, it means we need to do something about it. And with that background, it's important that we understand, number one, what's coming out of the catchments and moving into our subsurface and therefore groundwater. What happens to it once it's in the subsurface? Is it remediating itself? Is it biodegradable, or is it just going to persist in the environment? And where it ends up. So the freight and transport is an important step to understand what's going to happen once the contamination has entered into our subsurface environment. And there are various levels of treatments available for both in situ, which means you actually treat groundwater in the aquifer itself without pumping it up, or ex situ, where you pump the water, treat it, and then use it. But the level of treatment will vary depending on what you want to do with it. If you are using it for agriculture purpose, different level of water quality is required versus if people are using it for drinking and cooking. So I've been involved with large number of projects in India and elsewhere, but I'm going to focus on two projects which are relevant. The first one is relevant worldwide, because we have this problem everywhere, and the second one talks about remediation in extreme environment of Antarctica, because if we can figure out how to remediate groundwater in that kind of cold extreme environment, we can actually tailor back and find solutions for temperate regions. So I'll begin with the first one. The hydrological performance and pollutant control of tire-based permeable pavements. So if you attended the last session yesterday, we were talking about how we are dealing with issues in the water sector, that we have extreme floods on one hand and extreme droughts on the other hand, but at the other end we are also dealing with material and waste management. We have lots and lots of different types of waste and we need to do something about it. So in this project I'm trying to combine those two. So we talked a fair bit about circular management, and this project combines the circular management, water management and circular waste management. So urbanization causes generation of runoff as soon as it rains.
Okay.
So in a rural catchment, when it rains, a significant portion infiltrates to recharge our groundwater, but in the urban areas there is enough space available for the groundwater recharge. So soon after the rain, we start to generate surface runoff, which means our catchments get flooded much faster. So the permeable pavements are seen as a solution because, number one, we don't need extra space. We already have pavements and pathways in the cities. All we need to do is make them permeable. Okay? They will allow for groundwater recharge, enhance the base flows, and provide some treatment and reuse as well, as it used to happen in the natural catchments. And they reduce the peak flows, so help with flood protection. And in Melbourne, the other issue we have with our current concrete pavements is that all the pavement areas have strings of trees every 50 meters. So when the tree roots grow, the concrete pavements are rigid and they can't stand the growing roots and they just crack. So council is constantly replacing the pavements because they have been broken by the tree roots. So we were looking for solving the stormwater infiltration problem and also solving the growing trees problem. And that's where we started looking for alternate materials to concrete, which provides us the flexibility to accommodate root growth, provides the increased permeability to infiltrate the stormwater, and also provide some water quality benefits. So we combined it with another problem of waste tires, because there are millions of waste tires which are discarded every year and there is no other way than sending them to the landfill. So we are now working on creating the permeable pavements instead of just porous concrete, combining the concrete with the waste tire. So these waste tire based permeable pavements, they are flexible, they provide improved permeability, and they also provide flood protection and filtration because we can filtrate a lot of water through them. So this picture just shows that there is, on the top there are tire aggregates and the concrete, and we may use a polyurethane binder to bind them together and produce the permeable pavements from that. And as you see, this is one of the pedestrian pathway we have just put this material on. Moving forward, and that has been very successful. Moving forward, we wanted to increase the footprint of these permeable pavements, and we started looking at the possibility of putting them in the car parks. Mind you, because we are putting in waste tire, it adds flexibility and permeability, but that comes at the cost of reducing the mechanical strength of the concrete-based permeable pavement. So you can't put it on the roads. So it's not ready to put on the roads which has heavy traffic load, but car park provide a sweet spot. They still have some traffic load, but cars are just coming in, standing over and leaving. So these are two case studies we are working at the moment. One is in the city of Adelaide and the other one is Melbourne. So the left side, the city of Melbourne, the blue portions are showing all the car park bays which are installed with our material. The grey one is the actual concrete based, and we have done analysis on the water quality, the infiltration, and also the urban heat island effect of having the permeable pavements. The right hand side is the Melbourne one, and we are installing that, and the pictures below show the various steps of producing that. And you see different colors, because the next thing we also started to look at is if we change the color of the top layer, it also has impact on the urban heat island. So we are experimenting various combinations at the moment in Melbourne. Looking at, so when you use tire or any other waste material, the biggest concern also is it going to actually become another source of contamination? And plastic and tires, these things can actually leach out microplastics. So we are doing extensive surveys of collected stormwater from various regions in the city to see what kind of contaminants are going with the stormwater, as well as what might come out of these materials. So this is just a slide to show that we are going to focus on some heavy metals, total nitrogen and total phosphorus, because stormwater brings in a lot of nutrients depending on what the catchment characteristic is, total suspended solids and microplastics. And the current research focus is to look at what is coming out of the waste tire permeable pavement itself, what contaminant removal various combinations of those materials can provide, what is being removed. But then we don't expect that this material is going to remove everything. There might still be some residual contaminants, so we are working with various adsorbent materials. So you saw the top layer is the permeable pavement in the picture I showed a moment ago, but at the bottom, after the subgrade layer, we are now putting in various adsorbent materials so that any residual contaminants can be taken up by that. And we are doing detailed laboratory testing and the field testing on the site and developing some models so that we can predict the behavior if the stormwater characteristics change, what will be the outcome. So I think I'll stop here for this project. And we are also looking at larger side field monitoring for traffic loading. Even if it's car park, we are looking at when the cars come and go, the pathways in between which will carry most of the load, what happens to the mechanical strength. And I collaborate with professors from geotechnical engineering for that side of the things. And longer term water monitoring is going to be on the radar as well. So I'll be very happy to have a chat in the tea break, but I think I'll move on to the next project from here. It's a very kind of significant change of gear for this project. So that is right in the city, and this is in a pristine environment of Antarctica. So when you think of Antarctica, what you imagine is a very pristine, free of contamination environment, only blues and whites, but that's not actually the case. In Antarctica, most of the countries have established their research bases, and Australia has 4. And this is the site close to one of those research bases. So you see Old Casey Workshop. Casey is just the name of the station. So the workshop where we actually put together all the gear for the other research. New Casey Powerhouse, all the electricity generation happens through use of diesel, and there is a big powerhouse and there are always some accidental spills. And the Thala Valley disposal site is the site where all the kitchen and solid waste was dumped until the Antarctic Treaty came in late 70s. So once the treaty came in, it required all the countries to go and clean up the sites. And first response for Australia was, okay, we have some contaminated sites, we will dig everything, bring it back to Hobart and treat it here. What it resulted in though is, as you dig, all the immobilized contamination actually got mobilized, and the treaty also required that you can't really expand the scope of contaminated sites, so you have to treat it in a way that it remains contained. So that was not an option, and we looked at all the options, and most of the options for polar regions are not very attractive. So in the temperate region, if you look at the cost and time is much lower and you move into polar, I don't think my pointer is pointing very well. The blue triangle on the top shows anything you want to do in cold regions, you need much longer and at much higher cost. So permeable reactive barriers came out as one option which can provide the solution we are seeking for. And what it is actually, that you have a source of contamination, the drums, the oil drums on the top, and the orange yellow plume is the contamination plume. If you put a wall of chemicals and intercept that plume, anything that comes out will be cleaner. So that's the basic principle, that you place it in the path of the contamination plume. And it's designed to intercept the contaminated plume, but also it needs to provide preferential flow path. It has to have higher permeability than rest of the subsurface media, otherwise water will not move through this. And because we are talking about cold region where things freeze for 10 months in a year, they only pretty much thaw for 2 months of summer. It also needs to preferentially thaw before the rest of the media. And the bottom picture actually shows that we generally don't put a very large barrier, we put funnel and gate. So the wall itself is the chemical gate, and you put funnels behind it so that water is diverted. Just stop moving. Can you move it from there? Yeah, thank you. So as I said, the key issues in the cold regions are the kinetics become very, very slow. So whatever you can achieve in the temperate region, in those temperatures, the kinetics is very slow, and those soils are very deficit in nutrients. So there are no nitrogen and phosphorus supply available. So if we want to use any microbial remediation, we have to provide them nutrients and oxygen as well. The site hydrodynamics, because the barrier freezes over 10 months in a year, the hydraulic conductivity is very slow because of the clogging during freezing, and heat transfer in the PRB. So we have to solve that problem. We did put some heat trace which we could remotely control. So before the summer season started, we always have to turn the heat trace on, thaw the barrier so that when water starts to come in, it's ready to take on the water. And the other thing is interaction of bacteria with granular media. If you are talking about oil, you can actually use microbial degradation processes very easily here, but not in Antarctica. We're not permitted to use any introduced microbial flora or fauna. So we had to actually capture the existing flora and optimize the nutrient and oxygen requirements for them, and highly variable water and contaminant fluxes. Depending on, because of the climate change, those regions see those impacts much more clearly than we do. So 1 year there is a lot of melt, second year there is no melt at all. So the design has to be variable and able to accommodate the variability. So what we did is we kind of went in with that wall you just saw. It's a wall of chemicals, but we divided that into 5 sections because we wanted to test a lot of different combinations. After 3 years of rigorous laboratory testing in Australia, we wanted to finally take it to the field. And we have labs which run at 4 degrees Celsius, not quite at the sub-zero temperatures, but up to 4 degrees. And if you see the 5 kgs here, the first layer on the top in each one of them is nutrient release, because we wanted to use the microbial degradation along with the chemical treatment so that we can enhance the life of barrier. Because if it's just the chemicals, they will be exhausted after a while and you have to go dig it out, which is quite a logistical challenge in Antarctic environment. So we wanted to enhance it with microbial degradation, the nutrient release in the first layer in all 5. In the second and third cage, the little blue line is showing in those 2 cages we were also providing oxygen. In the other 3 we were relying on natural oxygen. And then the second layer, SAB is option. SAB is special Antarctic blend. It's a different kind of diesel. It's a lighter diesel, but it is basically source of energy. And the third one, because we are introducing nutrients, we didn't want that the residual nutrients which don't get used are discharged and now causing eutrophication. So the third layer is nutrients option in each one of them. And at the bottom, the 5 materials are the ones which we used in different combinations in the middle layer. And here is the picture. As you see, so this is a 5 meter long, 1.2 meter wide, 5 different combinations, and it's highly instrumented. We are testing remotely temperature, dissolved oxygen, the moisture, and we go there every summer and we actually take out the water samples from this little tube sticking out and auger the soil samples to see how the things are happening. So this is actually the initial one. Now we have much better handle of which materials and combinations are working best, and next to it we now have a barrier which has the optimal combinations instead of having the 5 different cages. And the 2 V-shaped funnels you see on the side are to basically divert the flow from the catchment. And yeah, I have just listed a couple of papers from this work, and with that perhaps I'll stop, but very happy to have questions or comments now or chat during the tea break.